Right, so this is 655 and it's a space truss problem. So that means it's a 3D truss problem here. Um, so at these supports here, they're connected by short links here, which these short links are two force members. So at that joint there where they connect, they can only have forces in the directions that the links are connecting. All right, so that goes for all the supports here at A, B, D, and E. Okay, so to solve this problem, we're going to do it in two steps. We're going to find the reactions first of all these points where they connect to these short links, and then move on to the method of joints to figure out FEF. So FEF, this top member here, FAF, which is this member here, part of this triangle, and FDF, which is this member here. Okay, so let's start with the reactions. Put this down a little bit. All right, so we're going to have our equilibrium equations. Let's just start out by summing the forces in the x and setting those equal to 0. Okay, so what do we have in the x? Well, we have bx, and I drew all these lines here in the positive direction of their axes as well. So we can just say that that's bx positive. What else? We have dx plus dx plus ex. And then we also have this 2 kilonewton force at the top, which is positive. It's in the positive x direction here. So positive 2 equals 0. All right. So that's 3 unknowns, 1 equation. So we can't solve that. So we have some of the forces in the y direction and set those equal to 0. So doing the sum of the forces in the y direction, we have AY, we have 3 kilonewtons, that's negative here, and I believe that's all we have. So we can figure that out. We can have AY is equal to positive 3 kilonewtons. Okay. So now let's sum the forces in the z direction, set those equal to 0. All right, so the z, we have bz over here. We have dz plus dz. All right, what other ones do we have in the z direction? We have 4 kilonewtons downward here, so that's negative 4. And that should be it. Okay, two unknowns in this equation. This is not directly solvable. All right, so we've had our sum of forces equals 0 in the x, y, and z directions. Now we need to move to the moments. So let's take the sum of the moments about the x-axis and set those equal to 0. And we'll call counterclockwise positive. So this is the x-axis here. All right, so since AY is right on the x-axis and BZ and BX are both on the y-axis, those are going to have no contribution to the moment here. In addition, DX being pointed straight in the x direction here is not going to create a moment around this x-axis. So let's write these out. Okay. So we have this 4 kilonewton force, okay, and that's going to create a counterclockwise moment, so that would be positive 4, and the distance that it acts away, if you do the geometry on this triangle, this distance here is 1.5. Okay, then we have this 3 kilonewton force at the top, and that's also going to create a counterclockwise moment, so that would be a positive. And the perpendicular distance, that is here, this vertical distance, which is 2.6. And going forward, we also have the dz force here, dz, um, and that's going to create a clockwise moment, so that's going to be negative. So dz, and the distance dz is acting away, is the full length of this, which is 3 meters. 3 meters. And that is equal to 0. All right. Sum of the moments now around the y-axis and set those equal to 0. Again, counterclockwise being positive. Okay, so we have this, here's the y-axis here. And we have this 2 kilonewton force, and it's going to create a counterclockwise moment. So that's going to be positive. The distance here, the perpendicular distance from the y-axis, is 2.6. Okay, and then we have this 4 kilonewton force here, and that 4 kilonewton force is going to create a counterclockwise moment around the y-axis, so that's also going to be positive, so 4. And the distance that is acting away is 5 meters, this total distance here, 5 meters. And what else do we have? dz is going to create a moment around the y-axis, and that's going to be a clockwise moment, so that's going to be a negative value there, dz, and the distance that it's acting away from the y-axis is 5 meters. And then we also have this EX up here, which is going to create a moment, and that moment will be a counterclockwise moment. So we have EX, and the distance that is acting away is this vertical distance here, which should be the same distance as in the front, which is 2.6 meters there. All right, and set those equal to 0. All right, now the moments around the z-axis and setting those equal to 0. We first have this dx, so the z-axis is here, right? So dx is going to create a moment that is counterclockwise. So we have dx, and the distance that is acting away from the x-axis is 3 meters. This distance here, 3 meters, or I'm sorry, from the z-axis is 3 meters. 3 meters there. And then we have AY here, and that's going to create a moment around the z-axis. And that moment will be, using the right-hand rule, that will be a positive moment. So we have AY, and that is acting a distance of 5 meters away, this distance here. And then we have EX up here. That's not totally obvious that it creates a moment, but it's a little ways off the z-axis here. This distance 1.5, and that's going to create a positive moment. So we have EX times 1.5. And then let's deal with the forces up here. The 2 is also going to create a moment, and that's going to be a counterclockwise moment at the same distance that X is acting away, is 1.5. And then we also have this 3 kilonewton force, which is going to create a moment, and that moment is going to be a clockwise moment, so that's going to be negative 3 kilonewtons. And the distance that is acting away is 5 meters. So now we have 6 equations, and we have 1, 2, 3, 4, 5, 6 unknowns. This system should be solvable with the equations that were given. All right, let me calculate this and we'll come back. Okay, so we found the reaction forces here, and I've listed them all here. So we've solved all 6 of those. And now what this problem is really looking for is I marked on the diagram here with pink which ones we're actually looking for. So we're going to proceed to do the method of joints. to solve for these. Now I'm going to start at point D, and then once we have point D, we should be able to move up to point F, and point F should then solve the rest of the problem for us. So let's start at joint D, and hopefully we can find this force FDF here. Okay. So I've drawn out joint D, and it gets a little confusing here, but I put the reaction forces here and here. This one's negative 0.5755, so the arrow is actually pointing the other direction, but I just left it this way and showing it as a negative number. So let's do the sum of the forces in the z direction. Okay, so the sum of the forces in the z direction, FDC and FDA are both not going to have any contribution to the forces in the z direction. And neither is this force here. So we have a positive 4.5981 plus a component of FDF, all right? And the vertical component, as we move from D to F, it goes up. Let's see, do we have that distance? Yeah, 2.6. So that's 2.6 in the vertical direction, and we know that the hypotenuse there is 3 meters. So 2.6 over 3, and that should be equal to 0. And solving that equation, we have FDF comes out to be negative 5.31 kilonewtons, which is then 5.31 kilonewtons in compression. And that's one of the forces we're trying to solve. We're not interested in FDA or FDC, so we don't need to do any of the other equations for this joint. Let's get the other joint drawn and move on. On to joint F here. All right, so joint F is up here, and we have a lot of members connected to joint F. We have 1, 2, 3, 4 members connected to joint F, along with these forces up top here that we need to include. CF or FC here, this member in the back here, is kind of an odd member, and I think we'll need the directions of that member. So I quickly found the length of CF, which is in the X direction we have 5, in the Y direction 1.5, and in the Z direction we have 2.6. So finding the hypotenuse using the sum of the squares, taking the square root of that, the total length of CF is 5.831 meters. All right, so here's joint F. We already figured out FDF. I didn't include any of the four external forces applied at F, but we can't forget about those. I just didn't include them on the diagram to keep things a little cleaner so we could see what was going on. So let's get moving. Take the sum of the forces in the X direction and set those equal to 0. All right, and if we do that, we have this 2 kilonewton force that we can't forget about. So we have 2 kilonewtons, and FEF is acting directly in the negative X direction here. So we have negative FEF. And then we need to, FDF and FAF are not moving in the, or have no components in the X direction, so we can exclude those. But we need to include FCF here. And that's going to be in the negative, it's pointed more so in the negative X direction here. So we have negative FCF here. And the component of that, so in the X direction we have 5. As we move from F to C here, it's 5. And over the total length of it, which we just found is 5.831, and that is equal to 0. And we have 2 unknowns in this equation. We can't solve that yet, so let's move on to the sum of the forces in the Y direction, set those equal to 0. So we have the external force in the Y direction of 3 kilonewtons, and it is pointed in the negative y direction, so that will be -3 there. Okay, and FEF is going to have no component because it's pointed in the negative x direction, directly in the negative x direction. So we have FDF, which is going to be the component of that, the projection of that is going to be in the negative y direction. So we have negative of a negative 5.31, and the component of that, all right, as we move from F to D, that length there is 1.5. So that's 1.5 over the total length of D and D to F, which is 3 meters. Okay. And then we'll have FAF, which will be positive FAF, and then the component of that in the y direction is again 1.5 over 3. Okay. So we have this one done, we have that one done. We don't have to worry about this. We have the external, and we need FCF still. And FCF will be pointed in the negative y direction, so that'll be negative FCF. And the component of that is 1.5, right? As we move from F to C, it goes negative 1.5 and over 5.831, the total length of CF, and set that equal to 0. Okay, and then lastly, let's sum the forces in the z direction and set those equal to 0. Okay, the external force in the z direction here is -4. All right. FEF is not going to have a component in the z direction, but all the other ones will, so let's work on this. FDF will be in the component will be in the negative direction. That's negative of a negative 5.31, and the component of that, so it moves down 2.6 meters over its height, length there is 3, and then FAF should be in the negative direction as well, FAF, and the component there will be the same as FDF, 2.6 over 3. All right, and then lastly FCF, and it moves downward in the z direction, and that is negative 2.6, so it moves downward 2.6 over its total length of 5.831. So we have 3 equations here, and we have 3 unknowns, FAF, FCF, and FEF. This is then solvable. All right, so simultaneously solving those equations, we went all through that trouble to find the components of FCF, but it comes out to be FCF is a no load member, so it's 0. FEF comes out to be positive 2.00 kilonewtons, and that is in tension then. And FAF is a positive 0.691 kilonewtons, and that is in tension. There we go. So we have now solved for all 3 of these members, and that is problem 655.